Yep, just now I was stopped at this point saying that if you want to get the maximum power and you are referring to this operation, then you should rotate your rotor ideally at this speed. Okay, not something lower and not something higher. Okay, so faster speed doesn't mean better. Yeah. Okay, in order to express the power efficiency of CP, just now the CP is what we call we use CP to express the efficiency of the extractable power, isn't it? So in order to express the power coefficient Cp in terms of both the upstream wind velocity V and the blade rotational velocity omega, a parameter called the tip speed ratio is defined. All right. So remember, we have incoming wind velocity, we given V, the rotational speed, okay, omega, and then this V is the what we call the um, is what we call the net effect of the rotational speed, considering also the radius of the blade, right? R. So V, this small letter V is equal to RW, and tip speed ratio is defined as this term divided by the incoming wind velocity. So omega is also equals to 2 pi over 60. 60 is a hertz. 2 pi n is the uh, RPM, okay, the rotational per minute of your plate. Okay, we'll see how we are going to apply the TSR later on. Yeah. So, so the power coefficient, just now remember, ideally we say that it is in between 0 and 0.4. Not ideally, practically, okay, in between 0 and 0.4. It can go somewhere higher depending on what type of blade you're using and what is your TSR. Take for example, yeah, if you are operating a high speed two blade type of rotor, to maintain the maximum CP, okay, at this point, the ideal TSR would be somewhere in between 5 and 6, let's say 5.5. So meaning that you have to adjust your rotational speed, remember, because TSR equals to RW over V, you have to adjust your rotational speed, the omega, in order to get a TSR of 5.5. All right. R is the radius of the blade, or you can also adjust the design of the blade. Okay, you can either increase the velocity or reduce the velocity depending on the radius of the blade. And then incoming wind velocity we cannot control, the capital letter V. Okay, we cannot control. We can only control these two things. R is fixed once you have designed it, and omega is something that we can change throughout our operation. So depending on different rotor, for example, if you are operating a Savonius rotor like this, to get the maximum CP of 0.3, which is a very inefficient rotor to use, then your TSR has to be less than 1, right? This is the tip speed ratio chart, right? And that explains the tip speed ratio. And now I'll remark, yeah, why we say that we use TSR to control, to express our CP rather than CP, because in TSR then we are able to relate directly to the operation of the rotor, for example, the omega and also the R. And by having this chart, by controlling the TSR, I can indirectly control the CP, right? So TSR is something that is more relatable to engineer, because something that we can see, which is the radius and also the rotational speed of the rotor. Yaw effect. So yaw effect, what is yaw effect? The wind at a given site is subject to rapid and frequent changes of direction. So wind can change direction, right? But to maintain efficient operation, the turbine propeller plane must remain perpendicular to the wind direction. And this makes sense. Okay, we want to always have the wind turbine to be perpendicular to the wind direction. And to achieve this, it requires that the turbine assemble to free to rotate about the vertical axis, meaning that you want the rotor to always turn. Okay, you want it to turn and always face the wind in a vertical direction. So a phenomenon that engineers call the yaw effect. Okay, when you try to make this turn, yeah, with good bearings, a machine can provide a swivel under the influence of a vane or a rather wheel mounted downwind. So a yaw